Precision watch manufacturing begins with a brass base plate. This base plate material is brass alloy with composition of 63% copper, 37% zinc, plus trace amounts of lead to improve machinability. Base plate thickness is 1.5 mm with precision requirement of plus or minus 0.01 mm. Base plate surface undergoes precision milling. Surface flatness requirement does not exceed 0.005 mm. This means across entire base plate surface, difference between highest and lowest points cannot exceed 5 micrometers, equivalent to 1/10 of human hair diameter. Such high precision ensures all components mounted on base plate maintain perfect coaxiality. Surface also receives mirror polishing treatment. Polishing uses aluminum oxide compound with particle size of 0.3 micrometers. After polishing, surface roughness reaches Ra 0.05 micrometers. Under microscope observation, surface is mirror smooth. This is not only for aesthetics. Smooth surface reduces friction, lowering energy loss. Base plate has dozens of mounting holes. Each hole diameter varies according to purpose. Smallest hole diameter is only 0.2 mm for mounting jewel bearings. These hole position precision requirement is plus or minus 0.005 mm. Drilling uses tungsten carbide micro drills with rotation speed reaching 80,000 revolutions per minute. Inspector carefully examines each hole quality using magnifying glass. Magnification power is 10 times. At this magnification, 0.01 mm error is clearly visible. Inspection content includes hole roundness, position accuracy, surface finish. Any discovered defects must be recorded and decision made whether rework is needed. Base plate weight also requires precise control. This base plate standard weight is 3.2 grams with allowable deviation of plus or minus 0.05 grams. Weight control is achieved through precise material removal. Base plate back has decorative Geneva stripes. These stripes are not only beautiful but also serve to reduce weight. Each base plate is engraved with unique serial number. Number is laser engraved with character height of 0.5 mm and line width of 0.05 mm. Serial number is used to trace all manufacturing data for this base plate, including processing date, equipment used, operators and others. This is an important component of quality management system. Mechanical watch precision largely depends on bearing quality. Traditional metal bearings have high friction and fast wear. Therefore, modern watches use synthetic gems as bearings. Used here is synthetic ruby with chemical composition of aluminum oxide, hardness reaching Mohs scale 9, second only to diamond. Each jewel bearing outer diameter is 1.5 millimeters, inner hole diameter is 0.2 millimeters, thickness is 0.4 millimeters. These dimension precision requirements are extremely high. Outer diameter precision is plus or minus 0.002 millimeters. Inner hole precision is plus or minus 0.001 millimeters. Such precision gems are produced by specialized gem processing factories using diamond tools for machining. Jewel bearings present perfect transparent red under microscope. This color comes from trace chromium ions with chromium content approximately 0.5%. Red color is not only beautiful but also convenient for identification during assembly. In some luxury watches, these ruby bearings are visible through transparent movement, becoming unique scenery. Installing jewel bearings requires extremely meticulous operation. Operator first grips gem with tweezers. Tweezer's tip width is only 0.1 millimeters with surface specially treated to prevent scratching gem. Tweezer gripping force on gem must be just right. Too little force causes gem to slip. Too much force may cause gem to crack. Jewel bearing seat is pre-machined on base plate. Bearing seat shape is precisely circular groove with depth of 0.4 millimeters and diameter 0.005 millimeters larger than gem outer diameter. This tiny clearance accommodates adhesive. Gem must sit perfectly in bearing seat with surface flush with base plate. Before placing gem, extremely thin circle of adhesive must be applied inside bearing seat. Adhesive used is UV curing glue with thickness only 0.01 millimeters. Glue application uses specially made dispensing needle with needle diameter of 0.05 millimeters. Glue amount must be precisely controlled. Excessive glue overflows, contaminating base plate. Insufficient glue provides inadequate bonding strength. Gem is slowly placed into bearing seat. Operator observes entire process through microscope, ensuring gem center hole perfectly aligns with mounting hole on base plate. Alignment precision requirement is 0.005 millimeters. When gem contacts adhesive, slight resistance is felt, indicating adhesive begins functioning. After gem positioning, flathead tool gently presses gem surface, ensuring gem completely conforms to bearing seat bottom while expelling excess adhesive. Pressing force is controlled at 0.5 newtons, equivalent to 50 grams weight. Then UV lamp illuminates for 30 seconds. Adhesive instantly cures. Gem is firmly secured. One movement typically requires installing 20 to 30 jewel bearings. Each critical rotation point requires jewel bearings to reduce friction. Installing all jewels takes approximately 2 hours. This process cannot be rushed. Each jewel must be installed perfectly. Luxury watches mark jewel count on movements such as 21 jewels. This is quality symbol. Mechanical watch core is gear system. This system comprises multiple precision gears transmitting mainspring energy to escapement mechanism, ultimately driving hands. Gear precision directly determines watch timekeeping accuracy. Here we assemble wheel train including center wheel, third wheel, fourth wheel and escape wheel. Smallest gear diameter is only 2 millimeters with 12 teeth. Each tooth height is 0.1 millimeters with tooth tip radius of 0.02 millimeters. Gears are manufactured from brass with nickel-plated surface to prevent oxidation. Gear weight is only 0.02 grams. Such light weight requires very precise balance. Gear machining uses CNC milling machine. Tooth profile adopts Involute design. This tooth form ensures constant velocity ratio during gear meshing with smooth transmission. Gear pitch precision requirement is plus or minus 0.003 millimeters. This precision is verified through gear measuring center using optical dividing head to measure each tooth position. Gear center hole is critical location. Hole diameter is 0.15 millimeters with precision of plus or minus 0.001 millimeters. This hole is for shaft mounting. Hole to shaft fit uses clearance fit with clearance of 0.002 to 0.005 millimeters. This clearance must ensure gear can rotate freely while preventing excessive radial runout. Before assembling gears, each gear requires cleaning. Ultrasonic cleaning machine is used with specialized watch cleaning oil at temperature controlled at 40 degrees Celsius. Cleaning time is 5 minutes with ultrasonic frequency of 40 kHz. After cleaning, compressed air drying. Air undergoes multi-stage filtration with cleanliness reaching ISO Class 5. First gear to install is center wheel. Center wheel diameter is 5 mm with 80 teeth. This gear is secured on center arbor. Center arbor passes through base plate. Minute hand is installed on center arbor's other end. Center wheel rotates once per hour. This rotation speed is reference for entire gear train. Using tweezers to grip gear rim, avoiding tooth surface contact. Tooth surface is gear working surface. Any scratches or fingerprints affect transmission efficiency. Align gear with center arbor descending slowly. When gear hole approaches shaft, slight resistance is felt from precision fit. Continue applying pressure. Gear slides onto shaft, producing extremely slight click sound. Third wheel meshes with center wheel. Third wheel diameter is 3.5 millimeters with 64 teeth. When installing third wheel, correct meshing with center wheel must be ensured. Center distance between gears is 4.25 millimeters with precision requirement of plus or minus 0.01 millimeters. Correct meshing should create tooth tip clearance of 0.05 millimeters between two gears. Method for checking gear meshing quality is gently rotating one gear, observing whether other gear follows rotation. Rotation should be smooth without binding. Simultaneously listen to gear meshing sound. Correctly meshing gears produce uniform subtle swish sound. If clicking collision sound occurs, meshing is poor, requiring readjustment. After all gear installation completion, entire gear train forms precision transmission chain. From mainspring barrel energy input through progressive speed reduction, ultimately driving escape wheel. Gear transmission ratio is precisely calculated, ensuring second hand advances 1 graduation per second, minute hand 1 graduation per minute, hour hand 1 graduation per hour. This precise time relationship is mechanical watch soul. Assembling mainspring requires specialized winding tool. Tool has clamping device for securing mainspring inner end with other end connecting to rotation handle. Operator secures mainspring outer end to barrel inner wall using tiny hook with hook diameter only 0.5 millimeters. After securing, rotation handle begins turning, winding mainspring coil by coil into barrel. Mainspring winding process requires extreme care. Rotation speed cannot be too fast, approximately 60 degrees per second, meaning each revolution requires 6 seconds. Excessive speed may cause mainspring kinking or fracture. During winding process, operator judges mainspring tension through tactile feel, ensuring tight fit between coils without excessive compression. After complete winding into barrel, mainspring presents Archimedean spiral shape. From center to edge, Gap between each coil is approximately 0.12 millimeters. This gap is mainspring thickness plus necessary clearance. Total coils range 15 to 20 depending on mainspring length and barrel size. Mainspring inner end connects to mainspring arbor. Mainspring arbor is shaft with diameter of 1.5 millimeters with square center hole for winding key insertion. Mainspring is secured to arbor through specialized connecting piece with thickness of 0.15 millimeters, fixed through riveting or welding. This connection must be very secure as it bears entire mainspring torque. Barrel also has gear ring located on outer circle of barrel body. This gear has 120 teeth with module of 0.15. Gear ring meshes with center wheel transmitting barrel rotation to gear train. For each barrel revolution, center wheel rotates 1.5 revolutions. This transmission ratio is carefully designed. Mainspring oil must be added inside barrel. Specialized mainspring lubricant is used with viscosity of 500 centistokes at 0 degrees Celsius and 80 centistokes at 40 degrees Celsius. This lubricant maintains stable lubrication performance across wide temperature range. Oil quantity is only 0.02 milliliters, approximately 1/10 of water droplet. After mainspring installation, pre-winding is required. Mainspring arbor is rotated approximately 10 turns applying certain pre-stress to mainspring. Then test mainspring release characteristics, measuring time required from fully wound to completely relaxed. Standard requires this time should be between 40 and 45 hours corresponding to watch power reserve. Mainspring fatigue life is important indicator. Quality mainsprings can withstand over 100,000 complete winding and release cycles. This means if wound once daily, mainspring can last nearly 300 years. Of course, actual use sees lubricant aging and other factors shortening this time, but mainspring itself has extremely long design life. Escapement mechanism is most precise and iconic part of mechanical watch. Its function is converting continuous rotation of gear train into rhythmic intermittent motion while providing energy needed to maintain balance wheel oscillation. Escapement mechanism precision directly determines watch timekeeping accuracy. Swiss lever escapement is used here. This is most mature and reliable escapement system. Main components include escape wheel, pallet fork and balance hairspring system. Escape wheel diameter is 3 mm with 15 teeth. Each tooth shape resembles small shovel specially designed for pushing pallet fork. Escape wheel material is steel reaching hardness of HRC 60 after heat treatment. High hardness ensures tooth tips do not wear or deform during long-term operation. Escape wheel tooth surfaces undergo precision polishing with surface roughness RA value of 0.03 micrometers. Such smooth surface minimizes friction loss. Pallet fork is Y-shaped component with length of 4 mm. Fork's two arm ends each have ruby called entry pallet and exit pallet. These two jewels alternately contact escape wheel teeth controlling escape wheel release. Jewel contact surfaces undergo special polishing forming specific angle called impulse angle with standard value of 52 degrees. Pallet fork arbor diameter is only 0.1 mm with both ends installed in jewel bearings. Arbor to bearing clearance is 0.003 mm. This tiny clearance allows pallet fork free swinging while limiting radial runout. Pallet fork weight is only 0.05 grams. Such light weight enables rapid response to balance wheel motion. Balance wheel is 6 mm diameter ring component. Outer rim is brass inertia rim connected to center arbor through 3 extremely thin spokes. Balance wheel design pursues maximum moment of inertia and minimum weight. Total weight approximately 0.15 grams with 80% of mass concentrated in outer rim. Balance wheel has hairspring. Hairspring is extremely thin spring made from nickel-based alloy with diameter only 0.03 mm equivalent to half human hair diameter. Hairspring is coiled into Archimedean spiral shape with 13 coils. Hairspring inner end is secured to balance arbor. Outer end is secured to hairspring stud, which is secured to movement bridge. Balance wheel and hairspring form resonance system. Its oscillation frequency is determined by balance wheel moment of inertia and hairspring elastic coefficient. This system's natural frequency is precisely adjusted to 28,800 times per hour, specifically 8 times per second, which is standard watch frequency. Each oscillation corresponds to second hand advancing 1/8 second. Adjusting escapement mechanism requires tremendous patience and skill. First, check escape wheel and pallet fork contact. When escape wheel tooth pushes entry pallet, contact should occur approximately 2/3 forward from tooth tip. Contact point too early or late affects transmission efficiency. Adjustment achieved through fine-tuning pallet fork position with adjustment precision of 0.01 mm. Then check pallet fork swing amplitude. Pallet fork swing angle should be 10 degrees measured with angle measuring instrument with precision of 0.1 degrees. Excessive swing angle causes pallet fork collision with banking pins too violently. Insufficient swing angle means balance wheel receives insufficient energy. Swing angle adjustment achieved through changing banking pin positions. Most critical is adjusting balance wheel amplitude. In fully wound state, balance wheel amplitude should reach 280 to 300 degrees. Amplitude is measured through timing machine. Testing machine receives watch ticking sound through microphone analyzing time interval between each tick calculating amplitude. Insufficient amplitude indicates inadequate power or excessive friction. Excessive amplitude may cause overbanking. During adjustment process, testing watch rate deviation in different positions is also required. Standard testing includes dial up, dial down, 3 o'clock up, 6 o'clock up, 9 o'clock up, 12 o'clock up 6 positions. Each position rate deviation should be within plus or minus 3 seconds per day. 6 position average deviation should approach 0. After complete escapement mechanism adjustment, crisp and uniform ticking sound is heard. This sound frequency is 8 times per second with stable rhythm and uniform volume. In quiet environment, this rhythmic ticking has extremely strong hypnotic effect. This is why many people enjoy listening to mechanical watch sounds for sleep. Movement bridges are protective structures covering above base plate. They not only secure and support various mechanical components but also embody concentrated watchmaking craftsmanship and decorative artistry. Each bridge's machining precision, surface treatment and installation technique represents brand's technical level and aesthetic pursuit. This movement has 5 main bridges. Largest is wheel train bridge covering center wheel, third wheel and fourth wheel. This bridge is forged from brass, material designation CUZN 37 containing 63% copper and 37% zinc. Brass possesses good machinability and moderate hardness approximately HB 90. Neither too soft causing wear nor too hard for difficult machining. Bridge basic shape is CNC milled. 5-axis machining center is used with spindle speed reaching 20,000 revolutions per minute and feed rate of 500 mm per minute. Bridge thickness is 0.8 mm with flatness requirement of plus or minus 0.01 mm. This means difference between highest and lowest points across entire bridge surface cannot exceed 10 micrometers. Bridge edges receive precision beveling. Bevel angle is 45 degrees with width of 0.3 mm. This bevel is not simple deburring but precisely calculated and machined decorative bevel. Bevel surface is polished presenting bright reflection line under light. This line is uniform and consistent without any wave or interruption, a hallmark of fine watchmaking. Bridge front receives Geneva stripes decoration treatment. Geneva stripes, also called cotes de Genève, is one of most classic decorative crafts in traditional watchmaking. These stripes are created through specialized polishing tool with tool head being circular grinding head approximately 2 mm diameter with surface coated in 1 micrometer fineness abrasive compound. Creating stripes, grinding head rotates at 3,000 revolutions per minute while moving linearly across bridge surface. Movement speed is 5 mm per second with pressure controlled at 0.5 newtons. Each stripe width is 1.5 mm. Adjacent stripes overlap approximately 0.3 mm forming continuous wave effect. Entire bridge has approximately 25 to 30 parallel stripes. Each must be straight and parallel without any skewing or bending. Stripe direction has strict regulations. In traditional watchmaking, stripes should follow movement radial direction, radiating outward from center. This is not only aesthetic consideration but also facilitates identifying different brand decorative styles. Each brand has unique stripe parameters including width, depth, and luster. Bridge backside equally requires careful treatment. Although back is mostly concealed after assembly, luxury watch backs undergo precision machining and decoration. Backside adopts perlage decoration, also called circular graining. Perlage comprises densely arranged circular patterns. Each circle diameter approximately 0.8 mm with circle centers spacing 1 mm apart. Creating perlage uses rotating round tool manufactured from brass with hardness slightly lower than bridge material being machined. Tool surface is coated with chromium oxide compound with particle size of 0.5 micrometers. Tool rotates at 10,000 revolutions per minute, vertically contacts bridge surface for 0.1 seconds, then moves to next position. Each perlage depth approximately 0.05 mm presenting soft diffuse reflection effect under light. Jewel bearing seats on bridge receive mirror polishing around perimeter. These circular areas diameter approximately 3 mm with surface roughness reaching RA 0.02 micrometers appearing mirror smooth under microscope. Polishing uses polishing wheel paired with diamond compound with particle size progressively reducing from 5 micrometers to 0.25 micrometers requiring 4 polishing processes. Bridge screw holes are critical locations. Each screw hole diameter is 0.9 mm with precision of plus or minus 0.005 mm. Hole inner wall is smooth with roughness of RA 1 micrometer. Screw holes have counterbores machined around perimeter. Counterbore diameter is 2 mm with depth of 0.35 mm. Counterbore purpose is accommodating screw head making screw head flush with or slightly below bridge surface. Counterbore bottom surface must be absolutely flat with flatness requirement of plus or minus 0.005 mm. Because screw head presses on this bottom surface, uneven bottom causes screw tilting resulting in uneven bridge stress. Counterbore edge receives slight beveling at approximately 30-degree angle with 0.1 mm width preventing screw head from scraping edge during entry. Before installing bridge, lubricant must be applied at specific locations. Jewel bearings require lubrication at contact surface between bearing inner ring and outer ring. Lubricant used is synthetic ester watch oil designated 9010 with viscosity of 120 centistokes measured at 23 degrees Celsius. This oil's viscosity varies minimally with temperature from 0 to 40 degrees with viscosity change not exceeding 15%. Oil application uses extremely fine oiling needle with tip diameter of 0.1 mm. Needle tip material is tungsten carbide with chrome-plated surface extremely smooth. Extracting lubricant from oil bottle, surface tension forms small oil bead on needle tip approximately 0.3 mm diameter. Slowly approaching jewel bearing when distance approximately 0.05 mm oil bead automatically jumps to bearing surface. This process requires only 0.1 seconds. Each jewel bearing lubricant quantity is 0.0008 milliliters equivalent to oil bead diameter 0.3 mm. Oil quantity control is extremely important. Slightly more or less affects movement performance. Excessive oil overflows bearing potentially contaminating other components or affecting escapement mechanism. Insufficient oil provides inadequate lubrication accelerating bearing wear. Gear meshing points also require lubrication using different lubricant. Gear lubricant designated 9015 with viscosity of 180 centistokes slightly more viscous than bearing oil. Each meshing point oil quantity is less approximately 0.0003 milliliters. During oiling, needle tip contacts tooth surface pitch circle position, actual contact region during gear meshing. Not every tooth needs oiling, typically every 3 to 4 teeth suffices as oil naturally distributes during gear rotation. After lubrication completion, bridge installation begins. First is wheel train bridge, the largest bridge. Bridge has 2 positioning pin holes diameter 0.5 mm matching positioning pins on base plate. Positioning pin height is 1.5 mm with diameter tolerance of plus or minus 0.003 mm. Positioning pin purpose ensures precise bridge position without any offset. Using tweezers to gently grip bridge edge avoiding contact with already decorated surface. Any fingerprints or stains require re-cleaning and re-polishing. Aligning bridge with base plate, 2 positioning pin holes align with positioning pins. Slowly descending bridge. When bridge approaches base plate, positioning pins enter pinholes producing extremely slight click sound. Continue descending until bridge completely contacts base plate surface. Check whether bridge is correctly positioned. Bridge and base plate should have no gaps. If pressing bridge forcefully, should not feel any looseness or wobbling. Simultaneously check whether various holes on bridge align with bearings below. This can be observed through holes. Arbor tip should be exactly at hole center. Bridge is secured through miniature screws. These screws are extremely tiny. Total screw length only 2.5 mm with threaded portion length 1.5 mm and head diameter 1.5 mm. Screw material is stainless steel with polished treatment presenting mirror finish. Screw head has slotted slot with slot width 0.15 mm and slot depth 0.25 mm. Screwdriver selection is crucial. Blade width must perfectly match screw slot with error not exceeding 0.01 mm. Too narrow blade slides at slot bottom, unable to effectively transmit torque. Too wide blade gets stuck at slot opening, potentially damaging screw head. Professional watchmakers typically have complete set of different specification screwdrivers from 0.1 mm to 3 mm 0.05 mm one specification. Screwdriver blade tip also requires regular maintenance. Blade tip should maintain sharp edge without burrs or gaps. Worn blade tip damages screw slot, causing screw unable to remove. Advanced screwdrivers use tool steel manufacturing with blade tip hardness reaching HRC 60, both hard and with certain toughness. Screw tightening uses precision torque screwdriver. This screwdriver has built-in torque limiting mechanism. Upon reaching set torque, automatically slips, producing click sound, prompting operator to stop applying force. This movement screw torque setting is 0.12 Nm, approximately equivalent to torque produced by 12 gram weight at 1 cm distance. Torque control precision is plus or minus 3%, meaning actual torque should be between 0.116 and 0.124 Nm. This precision is very important for ensuring bridge securing reliability and consistency. Insufficient torque may cause bridge loosening from vibration. Excessive torque may cause screw fracture or thread damage. Serious may cause bridge deformation. Screw tightening sequence is carefully designed. For bridges with 4 screws, diagonal sequence should be used specifically, first tightening diagonal 2 then another diagonal 2. This sequence ensures uniform bridge stress without one side tightening first causing other side lifting. Actual operation proceeds in 3 stages. First stage, all screws are gently threaded in, only tightening until screw head just contacts counterbore bottom surface. Torque approximately 20% of target torque, specifically 0.024 Nm. This stage purpose is letting all screws initially position. Bridge begins receiving downward pressure. Second stage, torque increased to 60% of target value, specifically 0.072 Nm. This stage bridge is further compressed but still has adjustment. If bridge position has deviation, slight adjustment is still possible at this stage. Third stage, final tightening to target torque 0.12 Nm. This stage each screw only degrees approximately 1/12 revolution. When torque wrench produces click sound, immediately stop applying force. Do not attempt to tighten slightly more. About right is unacceptable in precision watchmaking. After each screw tightening head, ideally screw head 0.05 mm. If screw head protrudes, if recessed excessively, may be excessive torque. Lightly touching screw head with finger. After all screw tightening is required. Using finger gently nudging center wheel, observing whether wheel train rotates smoothly. Under normal conditions, if rotation resistance obviously increases. Possible problems include excessively tight bridge installation, compressing bearing causing increased friction. Insufficient lubricant, changed gear meshing depth causing increased intertooth friction. Bridge deformation. Each problem requires careful analysis and solution, requiring watchmakers' rich experience and keen judgment. After wheel train bridge and balance wheel bridge. These two bridges are smaller. Escapement mechanism bridge secures pallet fork upper bearing. Balance wheel bridge secures balance wheel upper bearing. After movement assembly completion, it must be installed into case. Case is not only protective shell for movement but also guarantee of watch water resistance, magnetic resistance and shock resistance performance. Case material, machining precision and assembly quality directly affect watch service life and performance. This watch uses 316L stainless steel case. 316L is low-carbon stainless steel with carbon content below 0.03%, possessing excellent corrosion resistance. Steel also contains chromium 16 to 18%, nickel 10 to 14%, molybdenum 2 to 3%. This composition ratio makes steel rust-resistant even in marine environments, very suitable for watch case manufacturing. Case diameter is 36 mm, thickness 9 mm, weight approximately 40 grams. Case is manufactured through multiple processes, first forging, then CNC precision turning, followed by multiple polishing and brushing treatments. Case side adopts brushing technique, forming dense parallel patterns. Case front edge and lugs receive mirror polishing with mirror-like finish. Case interior is machined with space for accommodating movement. This space diameter is 29 mm with depth of 7 mm and tolerance of plus or minus 0.05 mm. Movement outer diameter is 28.9 mm. Movement to case fit is clearance fit with clearance approximately 0.05 mm. This tiny clearance facilitates movement installation while ensuring stable movement without wobbling inside case. Case bottom has O-ring seal. Seal ring is manufactured from fluoroelastomer. This material maintains elasticity across temperature range from -20 to +150 degrees Celsius. Seal ring cross-section diameter is 1 mm with compression amount of 25% after installation, compressed to 0.75 mm. Appropriate compression amount ensures seal ring effective sealing without permanent deformation from excessive compression. Movement case installation uses specialized assembly tool. Tool has pressing head matching movement outer diameter with soft material covering head edge, avoiding scratching movement decorative surface. First, movement is placed above case opening with positioning feet ensuring correct movement direction. Crown should align with crown tube hole on case side. Slowly press movement downward. When movement approaches case inner ring, slight resistance is felt, signaling seal ring compression beginning. Continue applying uniform pressure, gradually increasing to approximately 10 newtons, equivalent to 1 kilogram weight. When movement completely enters case, movement edge should be flush with case mounting shoulder with depth error not exceeding 0.05 millimeters. Check whether movement is correctly positioned. Through case back opening observation, movement should be horizontally installed without tilting. Crown stem should correctly insert into crown tube without binding. Rotate crown. Feel should be smooth with uniform resistance. If feeling rough or hearing abnormal sound, movement position is incorrect, requiring removal and reinstallation. Case back adopts screw down design. Case back is 32 mm diameter disc with fine serrations on edge facilitating tightening. Case back inner side similarly has O-ring seal with same specification as case bottom seal ring. Case back connects to case through thread. Thread specification is M31 with pitch of 0.75 millimeters. Case back tightening uses specialized case opener. Case opener has 3 adjustable claws with claw shape matching case back serrations. 3 claws simultaneously engage case back serrations rotating clockwise. Tightening torque requirement is 5 Newton meters. This torque is judged by operator experience. Insufficient torque causes inadequate sealing. Excessive torque may damage threads or overcompress seal ring. After case back complete tightening, case back marking should be in correct direction. Typically, case back is engraved with brand logo, model number, water resistance depth, and other information. This information should face case 6 o'clock position for convenient reading. To achieve this effect, watchmaker fine-tunes tightening angle and final stage requiring precise grasp of thread engagement state. After case assembly completion, entire watch presents complete form. Crystal uses sapphire crystal glass with hardness reaching Mohs scale 9 with multi-layer anti-reflective coating on surface. Through crystal clear crystal, white enamel dial and blued steel hands are clearly visible. Side brushing and polishing contrast demonstrates watch exquisite craftsmanship. Crown diameter is 5 mm with brand logo engraved on top. Crown surface has fine anti-slip patterns facilitating finger rotation. Pulling crown has 2 positions. First position adjusts date, second position adjusts time. Each position has clear tactile feedback without confusion. This precise positioning mechanism is also hallmark of fine watches. Strap connection adopts quick-release spring bars. Spring bar is 1.5 mm diameter stainless steel shaft with spring mechanism at both ends. Pressing one spring bar end causes other end to retract, allowing easy strap removal without any tools. This design facilitates user strap changing. One watch can pair with multiple different style straps adapting to different occasions. Case water resistance performance is verified through pressure testing. Watch is placed in specialized test chamber with water pressure gradually increased, simulating underwater environment at different depths. This watch water resistance standard is 100 meters equivalent to 10 atmospheres. Testing pressure exceeds standard by 25%, specifically 12.5 atmospheres for 10 minutes, ensuring sealing even under extreme conditions. After watch assembly completion, final and most critical stage is precision adjustment and testing. Regardless of how perfect previous processes were, if timekeeping is inaccurate, this watch cannot be considered successful. Precision adjustment requires professional testing equipment and experienced watchmaker. Testing uses electronic timing machine. This instrument receives watch ticking sound through microphone, analyzing time interval between each tick, calculating watch rate. Timing machine precision can reach 0.1 seconds per day, meaning it can detect watch daily rate deviation of 0.1 seconds. Place watch in front of timing machine microphone with dial facing up. Start testing. Timing machine begins recording watch ticking sound. Screen displays several key parameters. First is frequency. This watch standard frequency is 28,800 beats per hour, specifically 8 beats per second. Actual measured frequency should deviate from standard value within plus or minus 0.1 Hz. Second parameter is amplitude. Amplitude reflects balance wheel swing angle, also indirectly reflecting movement power state and friction situation. This watch in fully wound state should reach amplitude of 280 to 300 degrees. Insufficient amplitude indicates inadequate power or excessive friction requiring mainspring checking or relubrication. Excessive amplitude may cause overbanking, affecting timekeeping stability. Third parameter is rate deviation, also called daily rate. This is most intuitive precision indicator showing watch daily fast or slow seconds. Quality mechanical watch daily rate should be controlled within plus or minus 3 seconds. Swiss official chronometer certification standard is stricter, requiring daily rate within plus or minus 4 seconds with 5 position average deviation within plus or minus 2 seconds. Fourth parameter is beat error, also called amplitude difference. It reflects escapement mechanism working symmetry. Ideally, pallet fork leftward swing and rightward swing time should be completely equal. Actually, there is always minute difference. This difference should be controlled within 0.5 milliseconds. Excessive beat error causes unstable timekeeping with large deviation changes in different positions. If test results are unsatisfactory, adjustment is required. Most common adjustment method is regulator adjustment. Regulator is small component movable along arc track, changing hairspring effective length to adjust watch rate. Moving regulator toward fast direction shortens hairspring effective length, making watch run fast. Moving toward slow direction lengthens hairspring effective length, making watch run slow. Regulator adjustment precision is extremely high. Regulator has graduations, with each graduation corresponding to approximately 5 seconds per day adjustment amount. But actual adjustment often requires fine-tuning between graduations, with adjustment amount possibly only half graduation or even less. Using specialized adjustment tool through microscope observation, gently moving regulator, each movement amount may be only 0.01 millimeters. After adjustment, retest, observing rate deviation change. If deviation decreases, adjustment direction is correct. Continue fine-tuning until reaching target precision. If deviation increases instead, adjustment direction is wrong, requiring opposite direction adjustment. This process may require multiple repetitions. Each adjustment must wait several minutes for watch stabilization before retesting. For more advanced adjustment, testing watch rate deviation in different positions is also required. Standard testing includes 6 positions: dial up, dial down, 3 o'clock up, 6 o'clock up, 9 o'clock up, 12 o'clock up. Each position requires testing at least 2 minutes, recording rate deviation and amplitude. Ideal watch should have similar deviation in all positions with average value approaching 0. But actually, due to gravity effect on balance wheel, different position deviations always have differences. Watchmaker minimizes this difference, keeping 6 position deviation range within 10 seconds. Excessive position difference indicates poor balance wheel balance or escapement mechanism problems. Also test watch timekeeping stability under different power states. Starting from fully wound state, test every 6 hours until mainspring completely relaxes. Quality watch should maintain relatively stable timekeeping precision throughout entire power reserve period, with deviation change not exceeding 3 seconds per day. If watch slows significantly when mainspring nearly relaxes, escapement efficiency is insufficiently high. Temperature also affects watch precision. Hairspring elastic coefficient varies with temperature. When temperature rises, hairspring softens and watch runs slow. When temperature decreases, hairspring hardens and watch runs fast. Advanced watches use special alloy hairsprings with extremely low temperature coefficient, maintaining stability across wide temperature range. Testing measures timekeeping at 8 degrees Celsius, 23 degrees Celsius and 38 degrees Celsius, three temperatures confirming temperature influence within acceptable range. After all testing and adjustment completion, watch receives test report. Report details all test data including different position rate deviations, amplitude, beat error and others. This report proves watch has reached factory standard and is watch quality certificate. Finally, watchmaker signs or stamps on watch movement marking assembly date and number. This is watchmakers' recognition of their work, also assuming responsibility for watch quality. From now, this watch-carrying watchmaker's dedication and craftsmanship begins its time journey accompanying wearer through countless days and nights. Mechanical watch creation is art and science. It requires precision mechanical design, exquisite processing techniques, and watchmakers' years of accumulated experience and persistent pursuit of perfection. In this digital age, mechanical watch existence itself is romance. That rhythmic ticking sound is not merely time recording but hymn to human wisdom and handicraft. And now, accompanied by this gentle and regular ticking sound, our journey approaches conclusion. May these precision mechanisms and delicate craftsmanship guide you into peaceful dreams. Good night.
gentle hum from the heart of the machine. Warm currents pulse through circuits unseen. Low frequencies, breathing slow and deep. Metal whispers in the quiet glow. Sparks of rhythm softly start to flow. Exit shift like clouds in the dark. A symphony of cogs finding their spark. Atmosphere fades like a fading dream. The hum recedes into the machine. Warmth dissolves into the still serene. A gentle hum from the heart of the machine. Warm currents pulse through circuits unseen. Low frequencies, breathing slow and deep. Metal whispers in the quiet glow. Sparks of rhythm softly start to flow. Tessers shift like clouds in the dark. A symphony of cogs finding their spark.